Welcome, everyone. Well, I need some presentation there, I guess. Wait. Uh, yeah, okay. Welcome, everyone. Sorry for that. Hope you are having a great time in Bangkok. Well, for me, it's kind of sweaty and hot, but I kind of relieved from my back pain from that long time ago. Well, in blockchain, the bigger you are building, the stronger your security needs are. So Polkadot gets bigger each year and bigger each year. So the security knowledge need of the community as well. I'm Alpcan, and today we are going to deep dive into Substrate security with real-world examples from my own audits, and also end with practical fuzzing approach to Substrate security. Right now, I'm the lead security in analog chain. Before that, I was the Rust security team lead at Halborn, and I did bunch of Web3 and Web2 audits, penetration tests, and end-to-end security assessments and implementations. In our agenda today, we will go over these issues and end with practical fuzzing setup. So, to start, the basic issue, integer-related vulnerabilities, but we tend to see that as the most common issue still. Well, as you know, in Rust, when we reach an integer's limits, in debug mode, it panics, but in production, it just wraps around and creates some serious bugs or unintentional bugs. And also, if we try to cast an integer to a smaller type of integer, we can again trigger this issue, which is called casting overflow. The same logic applies with the underflows as well. If we reach the under limit, it again wraps around. And also there is one more issue with integers we tend to see a lot, which is precision loss. Since integers doesn't contain floating numbers, if we directly divide two integers together, we will just lose that hanging floating number, which can cause serious issues if there is economical calculations included. So you can see some brief examples of this. To a real-world example, in the first one, we have a trigger function which is called by off-chain workers to arrange their task trigger cycles. As you can see, there's a cycle parameter is taken and from the user side and put inside an unsafe math operation. And actually, this triggered some bugs in the testing. Yeah, and to remediate this, we just need to use safe math operations, and all will be fine. If there is a underflow or overflow, it basically panics at this point, like with a recoverable bay. And the second example is from a vesting schedule struct. And here you can see a daily vested tokens function, which calculates the vested tokens for daily. And as you can see, it just divides the total tokens into vested period directly, and we are losing some floating point integers here, which is important since we are doing economical calculations. And in order to prevent this, we need to use larger data models to scale them, and also define a scaling factor and multiply our divided number with that scaling factor and then divide it to save that floating number. Next one is the weight calculation disparity issue. In blockchain or in any program, the function consumes resources in terms of CPU and RAM. And in order to manage these resources, we need to, as a blockchain, introduce fees. And in Substrate, this is the weight fees. Weight fees are measured in picoseconds, which helps preventing spam by the attackers. And also, it helps maintaining a healthy resource blockchain environment. If if the fees are not calculated very well, or if there's a bug, then the fees can be bypassed. An attacker can just exploit this one to obtain unfair advantage, or slow down the network, or even may lead to denial of service inside the network. So here we have another example, which is an issue credentials function, which is used to issue credentials to the caller. And as you can see, it takes a credential vector of vector bytes. And the weight calculation actually at the first look seems fine because it's dynamic. However, there's a problem. Like, it only checks that outer vector of the credentials, but there is two vectors inside. It doesn't check the inner byte vectors. It doesn't actually check any kind of even inner byte vector. So an attacker can just simply send a one length credentials vector which has a really long byte array inside, which the weight fee will be really low since the credentials length will be just one. But again, the processed data will be really large, and maybe it can cause the denial of service or exhaust blockchain if an attacker spams this one. In order to remediate this issue, first we need to bound all of the vectors in this case, and also calculate the weight fees benchmarks dynamically, including the reads and write operations. And then also we can assume the worst case scenario in vector operations and just take the max value for that bounded vector. After the execution, we can always repay the client, the caller, back with the unused fees. And another example, actually I really like this example, like casting overflows in weight calculations. Again, we have a submit hash function here, which takes the hash value as byte array, which is not very healthy way. But if we check the weight calculation, well, again, it's really dynamic, and it seems there's no problem in there. Like, when the hash value gets bigger and bigger, the weight fee will also get bigger. But the problem is, as you can see, there's a casting operation, which casts the hash length to U32. So if an attacker just sends a value which has the length of U32 max plus 1, basically the submit hash weight calculation will reset, and they will be able to exhaust the blockchain in a really bad way. Actually, this is also saved in the storage, so it's a storage exhaustion as well. Well, again, in order to solve this one, we need to bound all of the vectors and make sure that there is no kind of integer errors in the weight calculation. And yeah, another well-known issue is the runtime panics. Well, runtime panics in the smart contract auditing are not very kind of big problem. At worst, it will just cause a revert. But in Substrate, they are really huge problems since it's a living layer 1 ecosystem. And if there is a runtime panic, bug, or vulnerability, and if an attacker or an individual mistakenly triggers this, it will basically can lead to a halt in block production if it gets triggered on many nodes, or at worst case, it will lead to a faulty block production. So an example here is that we have a submit price function here, which is used by off-chain oracles, where they submit a price of the asset ID. And as you can see, the function fetches the asset ID from the storage. And if it cannot find that asset ID, basically a runtime panic happens here. Actually, yeah, this one was not exploited, but some off-chain workers mistakenly caused panics here. And it took some time to figure out what's happening. Basically, we need to convert all kind of panics into recoverable errors. And also, we should avoid using unwrap on expect on Substrate, but use more kind of recoverable errors. And storage exhaustion. Storage exhaustion in Substrate can arise from attackers flooding the storage, spamming the storage, or it can arise from gradual accumulation of outdated data, just keeps together and gets bigger over time. And when this happens, the nodes will slow down, the synchronization time between nodes will slow down, new nodes will find it harder to join the network because of the storage needs. And also, yeah, in worst case scenario, it again leads to those issues. We have an update NFT metadata function, which takes an NFT ID and a new metadata from the client. And inside the function, it's basically kind of like burns the old NFT and generates a new NFT ID for the user, change the NFT ID of the user inside the NFT storage, and also updates, saves the new NFT ID's metadata inside the storage. But the problem is that it doesn't remove the old NFT ID's metadata from the storage. So over time, it will just get bigger and bigger. And since there is no way to remove it, a chain update might be required, which is something unwanted. And in order to remediate this, we need to remove unused data from the storage exactly when they're freed, or we can introduce storage deposits where users are paying in tokens for the amount of storage they are using, and when it's freed up, it's repaid. Yeah, insecure signature usages and implementations. These are my favorite vulnerabilities, I can say. Off-chain signatures are generally used in off-chain workers and also in cross-chain transactions where users signs data in chain A and sends it to chain B, and the chain B checks it if the signature is correct for authorization. And there is two kinds of issues with the signatures. One is replay attacks. If there is no kind of unique data for that task, or nonce value is used inside the signature, basically an attacker can read that signature from the chain and replay it and repeat that action in an unauthorized way, or in a worst case scenario, repeat another action in an unauthorized way. And the collision vulnerabilities, which we are going to explain a little bit more in more details, but basically they arise from not using delimiters between that signature variables. So when we are not using any kind of delimiters inside the signature creation, an attacker can play with that variables and create the same signature with different variables. We will examine it in a moment. Yeah, the first one is for signature replay. As you can see, we have a submit error function, which takes a task ID and error, and from the error, it creates a signature hash, and then checks if the signature is correct. Then just updates the given task ID as failed. Now, the problem is that it even doesn't take the task ID. So an attacker can just take the signature and just can replay it for other task IDs, which will make the other task IDs fail too. Yeah, to remediate this issue, we need to use signature specific variables like the task ID in this case, and also nonce values. Well, to the signature hash collision issue, this is like most of the security auditors, when it comes to signatures, only say that use unique variables, use nonce values. But we tend to see the hash collisions more and more while we are doing audits as well. What happens is we are continuing from the previous code. Like there is an append hash with test data, which creates a vector which gets converted into that signature hash. And it takes, in this case, the data, task ID, nonce, and cycle, which seems fine actually, because there is nonce value. However, when we check at the vector creation, it just puts all of the data next to each other without any kind of delimiters between them. So to explain with an example, here we have a data, which is, we can say error task ID 1 to 4, cycle 599 and nonce value 42. Like when we put it together, it will produce the same hash if the data is error task ID is 1 to 5 this time, and cycle is 9, and nonce value is 9 for 2. When we put them together, they basically create the same payload, and when we take this hash, it produces the same hash value. So an attacker can read a use signature, then arrange the values, and use the same signature for another task ID with another nonce. It's harder to exploit, but there is a huge risk. Yeah, in order to prevent this, we need to introduce delimiters. As you can see, we introduced a comma there between the variables, and now the vector is calculated with the delimiter, so those two payloads will not proceed processed as the same hash. And of course, we should be also careful with what kind of delimiter we are using. For example, if all of the variables here were string, again, it might be prone to hash collision issues. And out-of-memory management. Out-of-memory management issues in Substrate refer to vulnerabilities where the system runs out of memory. And it generally happens because of when the chain, the function, initialize a vector size or an array size from the user supplied input. And basically, it will lead to a panic and crash or other kind of similar things. And if we check an example here, as you can see, we have an allocation function. It's called with byte buffer, which takes an U size from the user side, and actually it checks the max buffer side, and if smaller than something, it allocates that size in the stack. But if it's bigger than something, it just allocates in the heap as a vector. So they just assume that nobody will send a really huge value which will overflow the heap. But normally they won't send, but an attacker might exploit this. So in order to remedy it, we need to check all kind of user supplied inputs before any kind of allocations. And the stack overflow, it basically kind of like the same thing with the out-of-memory management. However, this time we are overflowing the stack. And it usually happens from excessive loops and recursive calls, which goes really deep. And it again leads to program crashes and panic and unwanted situations. And I'm not going into very details of this issue, but we have a fetch sub0 function which uses a recursive call to go over all of the nodes, which is prone to stack overflow if the tree size is really big. So instead of using recursive functions, we should use iterative functions more, which is more safe. And if we must use a recursive function, then we must introduce a limit for the depth of the call. And XCM arbitrary execution, and denial of service issues. Cross-consensus messaging enables blockchain interoperability, but it also introduces some issues. Denial of service vulnerability can occur when attackers float a chain with excessive messages, overloading its capacities, and again, which will cause a slowdown chain or denial of service. And the arbitrary execution vulnerability is a bit more complex. It comes from lack of XCM configurations, allowing attackers to execute unauthorized operations on target chain, compromising its security and integrity. Well, from my personal audits, I actually didn't see these issues yet, but since the remediation are fairly easy, we can just directly go over the remediations. So the first one, we should introduce access controls, safe call filters, implement a restricted call filter that explicitly defines which calls are permitted and which are not, and from where they are permitted and from where they are not. And we need to introduce message filtering to remediate that arbitrary execution. So we should filter and allow only specific messages that we are going to use. And we should employ advanced filtering mechanisms to discard malicious XCM messages before they can consume the chain's resources. And other notable vulnerabilities is the insecure randomness. It's a hard problem to solve in blockchain, and it can cause serious issues if there is money involved, like a lottery system and so on. We need to use verifiable random functions in order to remediate this. And actually, PalletBabe already has this functionality, so we can use palette-based verifiable random function to generate random values. And the other one is vulnerable crates. Crates with known vulnerabilities can introduce vulnerabilities into our chain also. We need to regularly scan for vulnerabilities with cargo audit and update when it's necessary. And when we come to the fuzzing, so what is fuzzing and why we need it? Fuzzing is basically giving the functions a bunch of random data in a controlled way to see what happens. And also, it's generally in manual testing, we cannot think of all of the combinations, but in fuzzing, we are trying millions of combinations, so we can easily find any kind of, really hard to find panics or any kind of other kind of bugs. And in my idea, it's crucial to fuzz before going into live, and it's crucial to fuzz inside the development to catch these issues and remediate them before going to development. So from our approach, from security approach, the coverage guided fuzzing works best. This type of fuzzing monitors the program in each input to see which parts of the code are executed by that input. And if it can reach to a new code location, basically it feeds itself with that input and generates new input from that previous input. So it kind of feedbacks itself. Yeah, so it's really great to explore all the untested paths and aiming to maximize the code coverage and find deeper bugs. And if we are going to fuzz the substrate in a practical way, to set up the environment, we can use HonkFuzz. It's a compact tool to perform coverage guided fuzzing in Substrate. We can just install it with cargo install, then arrange and make a directory inside the palette or the crate that we are going to fuzz. Then we just need to include the crate and its dependencies into our fuzzer cargo town. Then we need to basically define the fuzzing logic, include the libraries inside the fuzzing logic, and then we need to write the fuzzing logic. So while writing the fuzzing code, we should be aware that we should parse the data. So here the data is just random. It can be like 1,000 lengths long, or it can be like 5 lengths long too. So we should implement some checks, then convert that byte array to the necessary data that we are going to use. And after executing our fuzzer, basically we are going to see we might see some crashes. And when we see that crash, we are just going to do a crash triage and just replay that crashing input to the program, and we will just see in which line and with which input the crash happens, and we can just directly look at it and understand why that crash happened. Well, that's all from my side. Thank you for listening, and if you have any kind of questions, you can ask now. Please.
Yeah, here's the microphone for you. one of your first slides where you described how people can stuff a lot of data into extrinsic parameters.
Yeah.
And it's a weight issue. So in our case, we don't like check the length of the parameters, but it's cryptographic pre-images which we're providing as parameters, and then we're verifying that data against the signature. Is that also safe? Because if the data doesn't pass signature verification, then we just reject the extrinsic.
Mm-hmm.
And that should be fine.
I think it can work fine, but of course, yeah.
I'll have to look
needs
deeper.
some checks. But it can be fine, yeah.
Yeah, okay. Cool.
You are using unsigned extrinsics or normal extrinsics?
No, we're using a signed extrinsic, but the data we're passing as parameters to the extrinsic, we verify that it's signed against another signature in storage somewhere.
Understand.
Yeah.
But I think it can be still prone to understand.
Yeah.
It will be fine. Yeah, it will be fine.
Sure.
Because it won't enter to the execution.
Okay.
Yeah. But of course it needs checks.
Yeah, I'll check it further.
Yeah.
Cool.
We can look at it afterwards.
Okay, so the guy on the back.
I saw in another one of your slides, of course, the suggestion to take bounded vectors as input.
Yeah.
I've seen few parts that like just a regular vector is taken and then just maybe checks for the max length are performed. Does it have any impact if we can bail out if the vector is longer? Like, so I think the length itself of the vector doesn't really affect the weight as long as we don't access storage or we don't do anything with storage, right?
It slightly affects, but yeah, it can be unseen because there is no kind of loops or storage usage. But still, it slightly affects because the function takes that input and processes it at the first. Yeah, it's just like I actually don't know about that one, but I think it will be fine. But still, like calculating weights dynamically with the vector's length would be a better approach. Yeah, please.
Okay, one quick last question, please. Yeah, for the guy in the back.
Nested vectors. So, like, if you have nested vectors, this happens if the extrinsic is accepted into the blockchain, you can batch up a bunch of extrinsic calls that have parameters that have nested structures. So, if it's a vec, as long as the encoded size isn't big, you can submit a transaction like with the batches, and so the entire batch, because it has to load the entire transaction, so all the batch. Yeah. And the extrinsics, it has to, before it even checks the weight, it actually has to process that and load it into memory. And all of those vec allocations, especially if it's nested, you can cause a large number of small allocations, and that puts pressure on the memory allocator. And so even I think even with a bounded vec, if you have a bounded vec containing a bounded vec, you can still do that pressure because you can do batch calls. So you have a bunch of batch calls. And each one can still be under a limit, so you get encoding. It still gets through the encoding for the bounded vec size, but you put pressure on the memory allocator, and you go over block time.
Yes.
We on Polymesh we had a permissions structure which had nested because we had palette permissions and extrinsic permissions, and so we had B tree sets. So we had a B tree set containing B tree set, and so we had like checks because we had limits on how many extrinsics and palettes you could have, but that was too late because the extrinsic was already accepted into the blockchain, and so you could build transactions and even span the network with a bunch of transactions, and so you can have a bunch of batch calls, and it has to load up each one individually.
Yes, I understand. I cannot quite understand the question, actually. I think you are just making a comment on the code, right?
Well, it's a it's putting pressure on the memory allocator because the memory allocator has to allocate individual, like every single vec has to be allocated. So you're putting, it's not really an out of memory, it's more of a CPU computation because it overloads the CPU computation and then you go over your block time. So the block weight doesn't account for it because the weights can't really account for it because you're putting pressure just on the memory allocator.
Yes.
Thank you. I think you can meet Nihat in the back. And,
we
get
can
some
talk
more
in the
information.
details.
Thank you,
later on.
Nihat.
Yeah, thank you so
you for your
much.
speak.
Have a great day. Have a great holiday.